introduce you to is this idea of how you see the ordered pairs written. It's a little different than what you normally see, and I know for some of you, functional notation is relatively new, and for others, it's a little bit old hat, so you have to be a little patient with me if I'm covering stuff that you've already know. But you're used to seeing things here like -3 in the actual value, but this is just to remind you that the output value, what you typically call y, is the result of putting -3 into this function and performing whatever operation this function says to do. In this case, it's taking the absolute value of your input. So notice here, instead of writing my two columns with x and y above it, I've put x and f of x, just so you start to get used to a little bit of this functional notation. And the only way you get used to it is seeing it and using it. So I'm going to put x and f of x, and when I put in -3 for my input, that tells me whatever my function says to do, I'm going to do. So I take the absolute value of each input and out pops 3. So again, most of you were able to successfully graph this function called the absolute value function. Now, throughout the next 3 classes, and actually the remainder of the semester, we're going to be referring to certain graphs as parent functions. There's certain graphs that before you leave here, you shouldn't even have to think about graphing. And those are the graphs that we call our parent functions. F of x equals the square root of x, the absolute value of x is one of our parent functions. So when you see that equation, that function, this picture should come to your mind. There's other parent functions as well. Here's another one. F of x equals x squared. That's a parent function. You should have that graph like etched into your brain. All these parent functions should be right there without much thought. Similarly, as you work through your packet, you see another parent function right here, the square root of x. Now, you may not know what the square root of x, the positive square root of x looks like right now, but by the time you finish this package, you will. That's another parent function. Okay, so we're going to identify about 6 of these parent functions. Another parent function is one that you're very, very familiar with, f of x equals x, which is a straight line with slope 1 going right through the origin. This is called the identity function. The identity function. That's another parent function. Okay, and we'll talk about the other 2 in a couple of classes. So just wanted you to have that language, which isn't on your handout, because I'll be referring to these as parent functions. Also for you to be more familiar with this notation. So what we're doing in these first 2 preview exercises is starting to introduce you to the idea that because where you want to start to go as a math student is to be able to look at the equation of a function and not have to graph various x and y values in order to understand what's happened to it or to actually get its graph. You want to have a picture in your mind of the parent function that it comes from, and then by learning what we're going to learn and what you're going to practice over and over again for the next 3 days, you're going to have an understanding of how does this graph transform. And these graphs can transform several different ways. The shape can stay absolutely the same, as you notice in number 1. The shape of my blue function has not changed when I become my red function. The only thing that's happened is I've literally picked up this blue function, and what have I done to it? Moved it down 4 units. Okay? It's in the language and transformation world is called this function has shifted down 4 units. Now, many of you have said that type of thing in your description here. So the graph in number 2 has shifted down 4 units. And we use Someone said, I think it was John said, places. And that's kind of a nice way to think of it too. Instead of units, it's shifted down 4 places. But the typical language that we use is units. So it's shifted down. Now, one of the ways you see that, which you wouldn't normally do because maybe you say, oh, this is really kind of clear to me, is what you're doing anytime you talk about a vertical shift. To compare what's happened, you literally draw a vertical line down through one of your x values. Okay, so I've drawn a vertical line down through my x value. Why? Because when something's happened vertically, notice your x value remains exactly the same. It doesn't change. So therefore, you compare what's happened to your output values. So whenever you're trying to figure out what's happened vertically, you draw a vertical line down through one of your x values, and you take note of what's happened to your output. Okay? The other thing, the other language that we use is that when we compare, let's call this red graph, I'm going to give it a name now. I'm going to call it G, function G. And can anybody think of what the equation for the function G would look like? If you know that f of x is the absolute value of x, what do you think would be the equation for the function G? What would that look like? If you could, yep, Ben?
Absolute value of x minus 4.
Okay, and I could write that a couple of different ways. So can you literally tell me what it looks like or show me on the board? Okay, so the absolute value of x, take away 4. All right, does everybody agree with that? Okay, and can you see this on the graph? You've put in a value of x. You've performed the operation on it. That operation is called take my absolute value. Everything that happens to that output happens afterwards, post-operation. So one way you can see that is you can replace the absolute value of x with a substitution. Do you see that the absolute value of x is called f of x? So you can write that like this. So my new function, g of x, my red function, I probably should have all of this in red. My red function is my previous function, f of x, with 4 subtracted from all of its output. So all the action, so to speak, all the action has happened post-operation. Let's compare that with what's going on down here with this other parent function called a basic parabola x squared. Anytime you have a function where all of your exponents are positive integers, we call this a polynomial, x squared, x cubed, x to the 4th, x to the 5th, any combination of those. You like these functions because the curves are always smooth, there's no holes in them, there's no gaps. And the domain of all polynomial functions is all real numbers. It's the whole number line called the x-axis here. So these are really kind of fun to graph. You don't have a whole lot to think about. You just throw in some numbers and you can get the shapes. They can get more complicated, as we'll see in a few weeks, but right now they're fun to graph. All right, now let's take a look at what's going on. How did you describe the relationship between graph number 5 and graph number 4? What language did you use here? Someone want to volunteer what they've said? Yep. Okay, so in this case, the graph, to get graph number 5, graph number 4 shifted which way? Right 2 units. So when you shift right, anytime you shift left and right, you're thinking of a horizontal change, right? And a horizontal change affects your input. So somehow your input must be affected when you come up with your new function. If we go back to the top and we talk about shifting down, our output has been affected. And you can see here that the output post-operation has been affected. So now when we think about creating a new function for this black graph, g of x, let's call it, I'm still going to square something, but what's going to change now is all going to occur before I square. It's happening to my input. My input is changing before I even perform my operation. So this is called a pre-operation change. And all pre-operation changes affect horizontal movement. So similarly to what we did up here with the first graph, if you want to see a vertical change, you drop a vertical line. If you want to see a horizontal change, you drop or you put a horizontal line through your graph. So you just pick any place horizontally and you just draw a horizontal line. Now notice on this horizontal line, it's my y values that remain the same, right? Black. My y values remain the same. It's my x values that have changed. So when you compare these 2 points, you're at the same height above the x-axis, and what do you notice? That you've moved to the right 2 units. And then when you take this point 2, 4, I put it in the wrong spot, 2, 4, and you compare it to 4, 4, you say, I'm at the same height, but my x value has increased by 2. And that's taken care of right here with this idea that the entire graph has shifted to the right 2 units. However, writing this part really messes with your mind. So let's take a guess. Okay, so let me take out g of x here. I'm in GeoGebra here. So here's x squared. Here's x squared on both graphs. Anybody want to take a guess as to what they think the equation is for the black graph if we've shifted 2 units to the right? Josh? X minus 2 squared. That's interesting. X minus 2, even though I've gone to the right 2. Well, let's try it out. That's the fun of using technology. They can do it for me really fast without. So let's see. So he thinks it's the quantity x minus 2 that's being squared, and that's going to shift it to the right. Well, let's see. Yep. Interesting. How many people thought it was going to be x plus 2 quantity squared? Oh, come on. A lot of you, right? So this is where, for the rest of the next 3 days, this is where most of your work is going to have to occur. And you can either memorize it or you can really try to understand it. And I'm here to help you to really try to understand it. Ben came in early and he asked me this question. Why is this x minus 2 squared? Why do I see it minus 2? And there's some ways I can try to answer that. You got to look at the visuals, you got to look at the numbers, and you have to see that to be here at 0, I'm not going to do it now because I'll end up talking to you about 1 million times over the next 2 days, next 2 classes. So this is the preview exercises. Let's move quickly to the demo. Most of this demo we can do really quickly, but I want to introduce you to a few new ideas as well. We know what x squared looks like, so you can quickly plot x squared, okay, on your papers. And if I make any mistakes putting these dots anywhere they don't belong, let me know. These little solutions, these ordered pairs, don't let the whole. All right, so there's f of x equals x squared. You have 2 ways you can label that. You could just put an f like that, or you could say f of x equals x squared. Either way. So what are we going to do to this? Now we're going to graph on our graphing calculator and then copy each graph onto the axis. If you have different colored pens and pencils, then doing each in a different color can help you. I strongly urge you not to put away any pens for the rest from now through Monday, because you will end up probably needing to erase at some point along the way. And things could get really complicated if you use pens. I have plenty of pencils here and colored pencils, so don't worry about it. So I'd prefer not to use a graphing calculator or GeoGebra at this moment, and instead use your intuition to do this, or perhaps what you've learned from your preview exercises. So can anybody look at number 1 here? Our new function that we're going to graph is our old function, x squared, and we're going to add 3 to x squared. Can anybody tell me what's going to happen to this graph right here without a graphing calculator? Yeah, Carlton? It's going to shift 3 to the left. All right, well, let's give it a shot. So let's do x. So what did we plot? -3, -2, -1, 0, 1, 2, and 3. And f of x, we've got plotted. F of x is 9, 4, 1, 0, 1, 4, 9. And now I want to graph g of x. So g of x simply says take x squared, which is the same as this column, right? This is my x squared column. G of x says take x squared and add, what was it? 3, and add 3. So I can look right at this column here. This is the same. F of x is x squared, and I can add 3 to all of my outputs. So let's see. If I add 3 to 9, what do I get? 12, 7, 4, 3, 4, 7, 12. So what would my points look like now? My x coordinates have stayed exactly the same. I just got a little lazy here and I didn't put in my x column one more time. I decided just to kind of get a little lazy here. So what are my new points on g of x? -3, 12. So let me go over to -3 and go up to 12. My next point is -2, 7. So I go over to -2 and I go up to 7. There we are. And -1 is 4. And 0, instead of it being 0, 0 is 0, 3. And then because this has even symmetry, I've drawn these 3 points right here to the left of the x-axis. It means it has points that are reflected on the right-hand side. So I go to the right one and I go up to the same height of 4. I go to the right 2, I go up to the same height of 7. I go to the right 3 and I go up to the same height as 12. So this is now a picture of my g of x. So Colin, you want to tell me what you think's happened to g of x now? It's moved up 3 spaces, right? So g of, yeah. Okay, that's all right. We're all learning here. It's fine, but this is how we discover what's happened, right? So now we've drawn g of x here, and in our own words, to get the graph of g of x, the graph of f of x, as Colin said, has moved up 3 units. All right. If h of x is in a different color like green, what do you think h of x is going to do? Move down. So I take each of these values and I move it down 4 units. So instead of at a height of 1 here, at height of 0, I go down 4. At 1, I go down 4. At 4, so I just take a couple of these and go down 4 units. And then I use my symmetry idea, and boom, I don't have to plot all those points because I've learned stuff about symmetry and now about transformations. So this is called H, the red is called G, and the black graph is called F. And to get h of x from the graph of f of x, I have what? Moved down, has moved down 4 units. Okay? So that's how you describe the transformations that you see from your graphs. That's how we use language to describe the transformations. Now we're going to verify this. Notice that in each of these 3, f of 0, g of 0, h of 0, our x value has remained the same. It's 0 for all of these functions. So if you were doing a table, it would look like this. Here's your x value. It's 0. We want to know f of 0, g of 0, and h of 0. That's what we're finding. Okay? G of 0, f of 0, and h of 0. So you can do that by either using the equation or looking at your graph. F of 0 is 0 squared, which is 0. G of 0 is 0 squared plus 3, which is 3. And h of 0 is 0 squared take away 4, which is negative 4. So now compare what you've written up here with what the actual values are when you keep x the same. Well, to get g, I'm supposed to go up 3, and notice that your y value going from the graph of f to the graph of g has increased by 3, so that definitely checks. To get the graph of h from f of x, it says move down 3 units. So when I keep my x value 0, my y value for h is the output value at 0 minus 4. It's decreased by 4. That certainly checks. Okay? So you have ways now of checking. I'm not going to do this. This you can fill in yourself. Let's talk about domain and range. So to do that, I want to take a little picture of this graph right here. So when we go on to the next page, we have it visually. So let me take a picture of this real quick, little snapshot. Let's make it a little smaller. So we can use it on the next page. Copy, and let's throw it over here so we can take a look. Paste. Okay, so here are our 3 graphs. So let's talk about the domain, the range, and for f, g, and h. The domain of f, remember f is the black graph. It's a polynomial graph. Do we have any restrictions on what we can put in here for x? Absolutely not. We don't have to worry about any positive even square roots or fourth roots or fifth roots. We don't have to worry about denominators being 0. As I say, polynomial functions, in this case a quadratic function, easy peasy, all real numbers. And in fact, all 3 of your graphs is a quadratic, so they all have the same domain, all real numbers. Okay, what about the range for f? Can anybody tell me in interval notation, describe to me what I write for the range of f? Paul? Okay, and what do I use for my symbols for interval notation? Yep, perfect. So perfect, thank you. What language describes this set of numbers? What language describes this set of numbers? It's interval notation. This is a set of numbers. What language versus using mathematical symbols describes that set? Greater than or equal to 0. All real numbers greater than or equal to 0. Yeah, and there's another term we could use without having to say greater than or equal anywhere in our language. What kind of numbers are greater than or equal? Natural numbers. Natural numbers start with 1. Whole numbers, yes, they are whole numbers. Whole numbers are non-negative numbers. So these are all your non-negative. The reason I'm saying that is people tend to say positive numbers because they forget the zeros included. So these are all, the set of all non-negative numbers. Okay, how about G? G now is which one? The red graph. What about the range of G? Shannon, can you help me with that? Bracket. Yeah. Okay. And what about H, the green graph? Eli? Right. Okay. So what do we notice? Has the transformation changed our domain at all? Nope. Has it changed the range? Yes. And that's because it was a vertical transformation. So the vertical transformation deals with your output values, which is your range, but the domain stays exactly the same. So let's look at something I've already done already. Rewrite g of x and h of x as a transformation of f of x. Now we've seen the transformation visually with the graphs. Now we want to see how we represent these transformations algebraically. So hint, remember f of x is x squared. The transformation that has occurred in each of these two pictures, the red graph and the green graph, happened after we squared the input. That's called post-operation. This changes the output only and represents a vertical transformation. So how could I rewrite g of x in terms of f of x? That's the language we use, in terms of f of x. Right now, g of x is written in terms of x. So this is in terms of x. We want to write it in terms of f of x. So how would I write that same expression, x squared plus 3, but using f of x? Ben? F of x plus 3. Because all I've done is where I've seen x squared, I've replaced it with what it's equivalent to, f of x. So I perform my operation of squaring my input, then I add the 3. It's like an afterthought. Okay? When you're an afterthought, you're a vertical change. When you're an afterthought. Okay, h of x equals x squared minus 4. So I want to try that one in terms of f of x. F of x minus 4. Okay, so here we have, folks, visual representation of transformation, an algebraic representation of the transformation. And now, if you had just some points in a table and you saw that your new function was your old function with 3 added to it, all you do is add 3 to your y value. So you take each of your y values from your original function, you add 3, and out comes your new output value. So now the corresponding points on your function g would look like this. -2, 7. -1, 4. 0, 3. And 1, 4. And 2, 7. So your class activities today will take you the remainder of the period, most likely. There will be no demo on Friday. It's a continuation of working these transformations. So over the next 2 days, you're going to be working individually, maybe with your groups. If you want graphing calculators, I can give them to you. There will be times you have questions and you're confused, but if you work through it, in the long run, it's going to suit you more than my just telling you what happens with each of these transformations. So have fun. They are fun. And I'll talk to you in a few minutes. Any requests for music?